Hey, 12th graders. We are moving on from geometric sequences and series to continue on with our theme of exponential modeling. And what you're going to notice is that all of these are exponential models, right? Geometric sequences and series are exponential models, and compounding interest, annuities, amortization, in other words, financial algebra. Whoops. Okay. So this is all financial algebra, also exponential. So that's all what we want to talk about with that. All right. So we've talked about earlier when we were talking last year, I think like this time last year, maybe a little bit less than a year ago, about simple interest. And simple interest is when you have something where you've like invested $100 with 5% interest added yearly. Now, yes, we see a percentage here, but it's not a geometric sequence. The reason why is because that interest is added yearly. What that means essentially is year one, you take 5% of 100, which is 5, and you add that to 100, which is 105. And then year two, your 5% is still of the original investment. So with simple interest, it's only 5% on your original interest, and then that just keeps getting added, right? So then it's 105 plus 5, which is 110. Year three is still that 5% from the original 110 plus 5, so 115. This is being added by 5 every single time, so this is an arithmetic sequence, right? So simple interest is an arithmetic sequence. You can see that simple interest would be more beneficial for if you have like a large initial investment. If you just want to put a super large initial investment in something and just keep it there for a long time, a arithmetic sequence or a simple interest might be a better option for you. Where your a sub 1 would be 100, your common difference would be 5, and all of that. Okay, compound interest is if you see that you've invested $100 with 5% interest, and you will see the word compounding yearly, or sometimes monthly, or sometimes bi-yearly, right? Quarterly. So if you see the word compounding, that means it's compounded interest. What that means is that they are recalculating that 5% every single year. In other words, they're taking 5% of the previous years. So you would do year one is 100 plus 5%, so 105, yes, but then year two is 105 times 5% plus 105, right? In other words, 105 times 1 plus 0.05. Hey, this is starting to look a whole lot like our geometric sequences, right? Compounding interest is a geometric sequence. So ... geometric, where our u or a sub 1 is 100, and this time our r is 1.05 because we're taking and recalculating that 5% every year and adding it back on. We have a formula for compounding interest. It's in your formula packet. It is the final value is equal to the present value times 1 plus r over 100 times k, close parentheses, to the kn. Where f of v, or sorry, not f of v, but fv is your final value, pv is your present value, R is your percent of interest. It will actually just be like, for instance, if your percent interest is 5%, it will actually be 5 in this formula right here. Notice it's because we already divide by 100. K is our number of compoundings per year. And N is our number of years. So that is how that formula works. If we wanted to, let's say, find out what the final value was for our compounding interest formula above, our final value would be our present value, which is the initial value, 100, times 1 plus R, which is 5, divided by 100 times K, number of compoundings per year. It says compounded yearly, so that's once per year, raised to the K1 times N. We don't know, right? It depends on whether we want it 5 years from now, 10 years from now, 2 years from now, right? That's our unknown here. So 100, that becomes 0.05, so 1.05 to the n power. So you'll notice it's very similar to what we know of as our geometric sequence. It just kind of simplifies down that way. Things to keep in mind: R does not get converted into decimal right away. It stays as that percentage. And K is that number of compoundings. Initial value here, just make sure you know what that value means when you set that notation. Okay, so let's just start putting it into practice. Jonathan invests 2,000 Australian dollars in a bank that offers simple interest at a rate of 3% per annum. Federico invests 2,000 Australian dollars in another bank that offers 2.9 interest compounded annually. This is a classic IB problem where they want you to compare and contrast geometric and arithmetic sequences. And they're doing that through simple interest and compounding interest. So we want to figure out how much Jonathan will have, which is going to be a simple interest. We want to figure out how much Federico will have, which is compounding interest. 3% simple interest per annum means that we need to know what 3% is if our A sub 1 is our initial value of 2,000. And then we're talking about simple interest, so we know that that's arithmetic. So maybe I'll write out my formula for arithmetic to let me know, okay, I have my A sub 1. I just need to know what my common difference is. And common difference is just going to be 3% of my initial investment, right? Up above, we said 5% of the initial investment was $5 because it was 100 times 0.05. So finding 3% of our initial investment is going to be 0.03 times 2,000, which is 60. If we want to know after 10 years, A sub 1 is the initial. And maybe we want to make a list to try and make sure that we are setting up our notation correctly. So A sub 1 is initial. A sub 2 would be 1 year later. A sub 3 would be 2 years later. So if I want 10 years later, I'm going to have to do A sub 11. Notice it's plus 1 of the years later. Okay, so I want A sub 11 equals A sub 1, which is 2,000, plus 11 minus 1 times 60. 11 minus 1 is 10 times 60 is 600, plus 2,000 is 2,600. So after 10 years, Jonathan will have 2,600 Australian dollars versus Federico, who has a different situation. We could use the geometric sequence formula, or we could use our compounding interest formula. Just because we just learned the compounding interest formula, I'm going to have you guys practice using that. So if we have a formula, let's write it out at the beginning. That's an important part of preparing before we solve. So we know what we need, what we're missing, and how we can figure that out. It says it's compounded annually, so K is equal to 1. We want after 10 years, so N will be 10. Our present value is the initial one, which is 2,000. And our interest is going to be 2.9, because remember, we don't turn that into a decimal. So we would just leave it like that. We can go ahead and calculate that all out. It gives us 2,661.85 Australian dollars. Okay, so the main thing I want you to get away from this example is the difference between simple interest and compounding interest, right? That at some point, compounding interest will supersede the simple interest, absolutely. So long-term investments, it makes sense that you would have compounding interest. And there's different formulas that you follow. This feels very, very familiar to our geometric sequences. However, it would, if it was a sub 11, right? We would have 11 minus 1, which is 10 up here. Our u sub 1 would still be 1,000, right? Or sorry, 2,000. So it feels very familiar to our geometric sequence, and it's because it is. They're all exponential models. There is this continuous relationship. It's just that compounding interest happens to cover this type of process. Okay.